In this video, we'll be discussing what the divergence series test is, its requirements, and how it's used to determine if a series diverges. The divergence test is a test that determines whether a series diverges. This is important because it's impossible to find the sum for the majority of series. Instead, we solve series problems by determining whether they converge, meaning they approach a set limit, or whether they diverge, meaning they don't approach a set limit. This test states that if the limit, as n approaches infinity, of a sub n does not equal 0 or does not exist, then the series of a sub n must diverge. If, however, the limit, as n approaches infinity, of a sub n does equal 0, then the test is inconclusive, meaning that the series could either be convergent or divergent. So why would we use a test that has a chance of being inconclusive? Well, we use the divergence test because it's extremely quick and simple to use. So now that we know what the divergence test is and its requirements, let's try out the divergence test on a problem. Okay, so here's our first problem. Before we can use the divergence test, we first need to take the limit of our series. So let's take the limit as n approaches infinity of 7n squared minus 6n divided by 4n. Now to make this easier to solve, we're going to isolate the dominant terms in the numerator and denominator. The dominant terms are the highest degree terms in both the numerator and denominator. In our case, it would be 7n squared in the numerator and 4n in the denominator. The reason why they're dominant is because the dominant terms grow much faster than the lower degree terms. For example, if n equaled 1,000 and we were to plug that into our equation for 7n squared, we would have 7 times 1,000 squared, and that's much bigger than 6 times 1,000. So now that we've isolated our dominant terms, we can start canceling things out. So the 7n squared and divided by the 4n, we can take out an n and get rid of that. That'll leave us with 7n divided by 4. And then from here, we can plug in our infinity. It's 4n, so 7 times infinity divided by 4. 7 times infinity, that's a really big number, so that's infinity. And then infinity divided by 4, that's also a really big number, so that ends up being infinity. And infinity does not equal 0, meaning that this series diverges. Awesome. Okay, so here's our next problem. Now this problem's a little bit different because our a sub n is -1 and it's being raised to n. And this is going to change our answer. But before we take the limit, let's just start plugging in values and see what we get at each index. So if we plug in n is equal to 1 into our a sub n, we'll end up with a -1. If we plug in and n is equal to 2, we'll end up with a +1. N is equal to 3, we get a -1, and n is equal to 4, we get a +1. And this is going to continue forever. Anytime we have an odd number, we're going to get a -1, and anytime we have an even number, we'll have a positive number. And if we were to try to visualize this on a graph, with a negative being at the bottom and a +1 being at the top, our function would first start at -1, it would reach +1, go back down to -1, go back up to +1, go back down and go up, and it's just going to keep doing this on and on and on forever until it reaches infinity. And because of this, if we were to try to take the limit, we wouldn't get anything. We would get does not exist. And this is because the limit doesn't approach anything. It's constantly changing. If we were to take the limit at this point right here, it would be approaching -1. But if we were to take it from here, it would be approaching +1. So because this limit, this function, doesn't approach a single finite value, it is impossible to take this limit. Therefore, it does not exist. So again, if we were to try to take the limit as n approaches infinity of -1 raised to n, we would end up getting does not exist. And does not exist does match one of the requirements for the divergence test. If our limit does not equal 0 or it equals does not exist, our answer, our series diverges. Here's our next problem. To solve this problem using the divergence test, we first need to take the limit as n approaches infinity of 1 over n. Next, we would replace n with infinity. But what does 1 over infinity equal? To understand this, let's start plugging in values into n. If we were to do 1 divided by 10, if we were to start off small, we would get 0.1. If we were to slowly get bigger, let's say to 100, we would get 0.01. If we did 1,000, we get 0.001. And if we did 10,000, we would get 0.0001. And as you notice, the larger our denominator gets, the smaller our value gets. And it's starting to approach 0. And that's our answer. As the denominator increases to infinity, it'll eventually equal 0 because it approaches 0. And if we were to draw this on a graph, we can see that as we keep going on to infinity, our graph starts to approach 0. And because our limit equals 0, our tests, the divergence test, turns out to be inconclusive. Now, that's not really a bad thing. It just means that our divergence test failed. But that doesn't mean that this series isn't divergent. It still has the possibility of being divergent. Okay, so here's our next problem. To solve this problem, we're going to take the limit as n approaches infinity of 9 divided by 4 plus the nth root of 3. Now, to solve this, we're going to simplify this nth root of 3. We're going to change how this looks. We're going to bring this over here. We're going to rewrite the nth root of 3 to be the 3 raised to 1 over n. And this is the equivalence to the nth root of 3. If you were to write the square root of x, the square root of x is equal to x raised to 1/2. There's an invisible 2 here. So all we did is just bring it to a fraction. And if we were to raise this n to infinity, if we were to bring it to infinity, we would get 3 raised to 1 over infinity. In the last problem, we just found out and solved that 1 over infinity is equal to 0. And 3 raised to 0 is equal to 1. So if we were to plug in infinity for the nth root of 3, we would end up getting 9 divided by 4 plus 1. If we were to simplify this, we would get 9 divided by 5. And because 9 divided by 5 does not equal 0, this series diverges by the divergence test. Okay, here's our next problem. To solve this problem, we need to use the divergence test. But before we do that, let's simplify our expression. If we look at our values, we'll see that we have a pi and we have an e, and they're both raised to n, with the only difference is that e is raised to negative n. We can simplify them by leaving our pi raised to n and by using the reciprocal of e raised to negative n to change the sign of e raised to negative n. If we use the reciprocal of e raised to negative n, we'll be left with e raised to positive n. And then from here, we can pull out the power on both of these used individually, and we can just raise the entire fraction by n instead. Now that we've simplified our expression, we can take the limits as n approaches infinity of pi divided by e raised to n. And then from here, if you were to raise it to infinity, you would get infinity. And because infinity does not equal 0, this series diverges. So here's our next problem. To solve this problem, we need to use the divergence test. And to use the divergence test, we need to take the limit of this expression. So let's take the limit of a sub n. We will take the limit of the, as n approaches infinity, of the square root of n squared plus 2 minus n squared minus 3, and this is the square root again. Now, to find the limit of something like this, of 2 square roots, you need to multiply by the conjugate. The conjugate is the exact same expression, except that the sign is flipped. So we're going to be multiplying by the square roots of n squared plus 2 plus, not a minus, a plus. If this was a plus, then it'd be a minus, but because the original expression is a minus, we'll multiply the opposite sign, which is a positive, plus the square root of n squared minus 3, and we also need to multiply the denominator by this. So another n squared plus 2 plus the square root of n squared minus 3. And then from here, this equals in the numerator is equal to n squared plus 2 minus n squared minus 3. And this is because both of these multiplied against each other just gets rid of the square roots. And then in the denominator, we are left with the square roots of n squared plus 2 plus the square roots of n squared minus 3. And now if we were to simplify this, we can see that there's a positive n squared in the numerator and there's a negative n squared in the numerator, and these two will actually cancel. This will leave us with a positive 2 and a negative 3. If we subtract those or add them together, we get a negative 1. And we will divide everything by n squared plus 2 plus the square root of n squared minus 3. And I'm forgetting to say, but these are under the square roots. And if you look at this, there's no n in the numerator, meaning that the dominant terms are in the denominator. And because we have an n in the denominator, that means that eventually, if we were to multiply everything out, if we were to plug in infinity for n, we would eventually get negative 1 divided by infinity. The negative doesn't matter. Anything divided by infinity is going to equal 0. And because this equals 0, this series is inconclusive. Here's our last problem. This problem's a little bit different because it involves trigonometric functions, but that won't really be a problem. So if we were to take the limit as n approaches infinity of arctan 1 over n minus arctan of n, we can set this can be equal to arctan. If we were to plug in infinity for 1 divided by n, we would get 0, because 1 divided by infinity is equal to 0, minus arctan of infinity. Now, to finish solving this problem, you need to know what the graph of arctan looks like. The graph of arctan looks kind of like this. It's got two asymptotes, and its function follows a path like this. It's a bit more swiggly. And this top line up here is equal to pi over 2. And this is approaching infinity. So as arctan approaches infinity, it'll eventually reach pi over 2, meaning that this arctan to infinity is equal to pi over 2. And arctan of 0 is just 0. So this limit is equal to 0 minus pi over 2. And this is equal to negative pi over 2. And negative pi over 2 does not equal 0. Therefore, this series diverges.